In question 4, we're given a first-order differential equation, dy dt equals 9y squared minus y cubed minus 14y, which we're explicitly told is an autonomous equation. So in other words, t, the variable t, doesn't appear explicitly in the differential equation. We want to find the fixed points of this autonomous equation, and then with justification, we want to determine the stability of each of those fixed points. So in other words, are they unstable fixed points, or are they stable fixed points, or what you might call asymptotically stable fixed points? Then we want to figure out what's the long-term behavior of the solution under 3 different initial conditions. So in other words, what would happen to the solution y of this differential equation as t goes to infinity if these are the starting points of that solution? All right, so we need to start, as the question indicates, by finding the fixed points. The fixed points would be any value of y which make the derivative equal to 0. So in other words, I'm going to set the right-hand side of this equation, 9y squared minus y cubed minus 14y equal to 0. I've got a little bit of factoring to do there. Let's pull out a negative y and then do a little bit of rearranging. So I'll have negative y outside of y squared minus 9y plus 14 equals 0. And now I can factor that pretty easily. Y squared minus 9y plus 14 is going to be y minus 7 times y minus 2. So I get 3 solutions. Y could be 0, so that's a fixed point. Y could be 7, so that's a fixed point. Y could be 2. So these are our fixed points. Okay, that's the first part of the problem. Now we want to determine, with justification, the stability of each of these fixed points. So the easiest way to do this is to sketch the graph of the function that represents dy dt. It's a cubic function, but we don't really need to know too much about it. All we need to say is that if we're plotting dy dt against y, the fixed points we just found have to be the intercepts of the y-axis, which in this case, notice, is the horizontal axis, not the vertical axis as we would usually make it. So I can pick out y equals 0, and y equals 2, and y equals 7 as intercepts through the horizontal axis. And then because this is a cubic function, I know this is either going to start in the upper left and bounce through those intercepts and head down to the lower right. It would do that if the leading coefficient were negative, or it could start in the lower left, bounce around and head off to the upper right. That would be true if the leading coefficient were positive. In this case, the leading coefficient is -1. It's the coefficient of y cubed. So it's the first of those two situations that I've described. So we don't need to worry too much about the exact details of this plot. All we really need to get a sense of is where is that function above the horizontal axis. So in other words, where is dy dt positive, and where is it below the horizontal axis? Where is dy dt negative? And so specifically, if I look at the intervals created by my fixed points, when y is less than 0, dy dt there is positive. So that would tell me that my whatever y is representing, it would be increasing as long as y is a negative number. Between 0 and 2, dy dt is a negative number. So y then would be decreasing. Between 2 and 7, y is increasing. And then, just enough room to squeeze it in there, for y bigger than 7, we're back to being decreasing. So, if I take the fixed points in ascending order, y equals 0, that's a stable fixed point. And it's stable because if y is slightly less than 0, y increases. So in other words, it moves towards the fixed point. And if y is slightly greater than 0, then y is decreasing, which again means it moves towards the fixed point. So y equals 0 is a stable fixed point. Y equals 2 is an unstable fixed point. Because, again, I'm going to be writing a lot of the same things over again here. In this case, if y is slightly less than 2, then y is decreasing. So it's moving away from the fixed point. And really, I guess I could stop there, because if you've got solutions moving away from a fixed point on either side, that's really enough to make it unstable. But I can be a little bit more complete here, and I can say if y is slightly greater than 2, then in that case y is increasing. Again, moving away from the fixed point. And finally, y equals 7, well, that's basically a carbon copy of what we just said about y equals 0. So y equals 7 is also a stable fixed point for the exact same reason. That's true because, again, if y is slightly less than 7, then we can see in that case y would be increasing, moving towards the fixed point. And if y is slightly greater than 7, in that final interval that we just drew on the graph, then in that case, y is decreasing. If it helps, by the way, something I should have done earlier is we could always take that information and represent it as what's called a phase line, which gets rid of the graph of the cubic and just basically brings it down to the fixed points and the direction in which y is moving on each of those intervals. So I've added that to the solution now as well, if that helps you understand what's happening, the way y is evolving a little bit better. All right, so we know we've got 2 stable fixed points, 1 unstable fixed point. That brings us to the final part of the problem, which is asking us for the long-term behavior of the solution in 3 different cases. So let's see. If y of 0 equals 1, then the limit as t goes to infinity of y, well, let's see. That means that we're starting in this interval between 0 and 2. In that case, we can see that y is decreasing there, and so it's being attracted towards the nearest fixed point, which is at y equals 0. So if y of 0 is 1, then the long-term behavior, the limit of y as t goes to infinity, is that y is going to head towards 0. If y of 0 equals 2, then that means it's starting right on that fixed point. And the whole reason it's called a fixed point is that if a solution starts there, it stays there, even, as in this case, if it's an unstable fixed point. So the limit as t goes to infinity of y of t in this case is equal to 2. And finally, if y of 0 equals 3, now we're a bit bigger than that unstable fixed point. So that means it's going to be repelled away from the unstable fixed point. It's in an area where y is increasing, and it's going to increase all the way towards the nearest fixed point in that direction, which is y equals 7. So if y of 0 is 3, then the limit as t goes to infinity of y of t must be 7. That's question 4. I'll see you in the video for question 5.